Okay, first of all, thank you so much for giving me a nice opportunity to talk about my ugly ducklings. So as you see from the title, today I want to discuss the seemingly ugly ducklings, which eventually turn out to be beautiful swans. Taking the physics examples in the top quark sector, mostly based on these series of papers listed here and some works in progress. Okay, I believe all of you guys know the story of the ugly duckling pretty well, which is about homely little bird who suffers from the abuse and bullying from the others around him until he matures into a beautiful swan. Okay, so in this talk, I want to talk about would be considered ugly ducklings in particle physics, and how to use transform them into beautiful swans for us. Okay. So getting back to physics, as you know well, the first one of the LHC was so successful in the sense that it discovered Higgs particle, which is the missing piece of the standard model. And it also rediscovered the standard model with great precision. So everything seems quite consistent with the standard model prediction so far. But as you know, the standard model itself has some unexplained issues like neutrino mass, dark matter, gauge hierarchy puzzle, etc. So many new physics models have been proposed so far, okay, including supersymmetry or extra dimension. But unfortunately, none of the new physics signature have been observed. Okay. Okay, that's fine. Presumably the second one of the LHC will be marked by not only precision studies, but searches for small signals. Okay, so obviously it's great that precision measurement will be done by different approaches or methods, as well as conventional techniques. And when it comes to a new physics search, okay, so as I said just before, it could be a small signal search, okay, just like the searching for buried Arkansas out of tons of treasure in a Hollywood movie, The Hobbit. So I'm pretty sure you guys know about Hobbit.
Yes.
Right? Okay. So in this context, I think any new ideas or approaches will be more than welcome, which are expected to provide different systematics or facilitate the discovery of new particles. Okay? So then the question is, what would be ugly ducklings in physics? So this is purely based on my personal point of view. Okay? So you can think of some variables, approaches, or techniques which could be considered as problematic, not useful, or not well under control. Of course, depending on your questions or channels at hand. Okay? So that you may want to avoid disregard or use them with the prescriptions to remove such problematic issues in a relevant analysis. Okay? So given those, the variables, approaches, or techniques, my claim throughout this talk is that with the different the perspectives or with careful study, such ugly ducklings in physics can be reborn as beautiful swans for us. Okay, so hopefully this statement can comprehend the seemingly uncorrelated topics in my talk within a single script. Okay, so here's the outline of my talk. So in the next slide, I'm going to briefly review why top sector is important, okay, and identify, the three ugly ducklings in the top sector physics, okay. So once this prelude is done, I will discuss them by the order of energy distribution, extra radiation, and missed bottom tagging. Then I will conclude my talk. Okay, so why is top sector so important? Okay. So needless to say, as you know, the LHC can be considered as the top quark factory. Okay. So for example, so about 300 billion the top pairs can be produced at 14 TeV with the integral luminosity of 300 inverse femtobar. Okay. So in other words, we have a great chance to discover something in the top sector in the future. And second, we know top pretty well in the sense that the top properties have been well measured since its discovery at the Tevatron. Okay. Nevertheless, there are still rooms for new physics to hide in the top sector. Okay? For example, the relevant decay width comes with the large fractional errors. Okay? And also, as you know, the largest quantum fraction to Higgs mass comes from the top quark. Okay? So that this top sector is highly promising as a window to peep into new physics. Okay? So for example, you can think of new physics in the production level, faking TT-bar signature. Okay? So in this case, large statistics enables you to constrain or rule out the new physics models in the relevant parameter space. Okay? Also, you can think of new physics in the decay level by rare top decays. Okay, so again, large statistics guarantees better chance to have new physics signals in the future. Okay. So given those motivations, then what would be the ducklings in the top sector? So as I advertised at the beginning, so I want to introduce three siblings here. So the first one is energy distribution, which is obviously not Lorentz invariant. Okay, so due to this frame dependent nature and unawareness of the initial longitudinal momentum at the hadron colliders, these energy variable has received less attention than other transverse quantities like transverse momentum. Okay. And the second one I want to introduce is extra radiation, mostly via QCD activities. Okay. So, well, this beast actually is not easy to the handle compared with the corresponding two-level process. Okay. And the last one I want to talk about, probably very briefly, if time allowed, is missed bottom tagging, mostly faked by charm quark. Okay. So as far as I understand, this is easy to distinguish from top and bottom initial jets. Okay. Okay, let me start from the energy distribution. Okay. I'm gonna briefly review the basic of the principle, and then move on to the new updates. Such as next leading order effects or detector issues. Okay. So here's the motivation. So let's imagine a simple two-body decay of a heavy resonance particle B into a particle A, and massless particle, which is visible, particle A. Okay. So actually, the argument, the details of the particle A, this guy, doesn't matter. Okay, so just forget about this guy. So then it is well known that the energy of the visible particle A is actually fixed and given by a simple function of the masses in the rest frame of particle B, right? So this is the expression. And here E star is the energy of the visible particle measured in the rest frame of the particle B. Okay? So then, if this E star is measured, and if you know the mass of the particle A, then you can easily measure the mass of the particle B, and vice versa. Right? So in that sense, this information is very useful, and it's great to be on this special frame. But our life is not easy, right? So in the left frame, this energy of the particle A should be Lorentz transform. Okay, so obviously it depends on mass parameters plus unknown boost vector and unknown emission angle of the particle A from the axis of the boost direction. Okay, so here's the formula, as you know. And you can easily see that the relevant energy distribution is no longer fixed. Okay, it's actually given by a function of the boost vector and emission angle, so that it becomes a distribution. Okay, so then you might say, okay, so nice information is lost. But my claim here is that it's too early to get disappointed. Okay, because it turns out that the peak of such an energy distribution is exactly the same as the rest frame energy, the E star. Okay, so let me get the proof. So just remember the Lorentz transformation formula here. So if the mother particles are scalar or produced in an unpolarized way, then this cosine theta becomes flat. And in turn, the energy variable is also flat for a fixed boost vector, okay? Just by simple change, okay? So schematically, the distribution is given by a rectangular shape. And if you look at Lorentz transformation formula more closely, then you can easily see that the given a rectangular distribution, the lower bound is actually smaller than E star, while the upper bound is bigger than E star for any boost. Okay? So no other energy value gets larger contribution from a given boost than does E star, and no other energy value is contained in every rectangle. Okay? And another observation you can make is that this distribution is asymmetric with respect to E star. Okay? But anyway, the main message is E star is included in common for whatever rectangle is given. Okay? So to get the energy distribution, you have to sum up the contributions from all relevant boost vectors. Okay? So in other words, you have to simply stack up rectangles weighted by boost distribution, which is kind of Lebesgue type integral. Okay? So then you can easily see that the energy distribution has a unique peak at E star. Okay? Then you may wonder what boost distribution I have in mind. Okay? But it turns out that the details of the boost distribution don't matter. Okay? So you can think of from descent, rise, and fall to a very crazy the boost distribution. But surprisingly, whatever boost distributions you assume, the peak should be the rest frame energy value. Okay, so that's the message. And let's see, here's the movie clip for you. Okay, so E star must be the location of the peak. Hopefully, this video clip convince you guys that E star is invariant. Okay. Okay, so to prove the concept, we take the example of the top quark decay, and then look at the energy distribution of the bottom quark. Okay, so definitely bottom quark is not massless, right? But then you can easily see that the bottom mass is really negligible compared with the top mass, right? So then the peak is not expected to the shift from the theory expectation. So as you see from this figure, okay, so the location of the peak is consistent with the theory expectation here, okay. But then you may still argue that maybe this is kind of an accident in this LHC 7, okay.
How crucial the depends on the assumption of the matter particles are polarized, which is the flat distribution.
Yeah, so that's crucial assumption. So if the matter particles are produced polarized way, like a W, right, then this argument doesn't go through. So that you can't guarantee that the location P is actually consistent with the residual energy value. So it's highly model dependent. But then fortunately for the top, they are produced by mostly QCD. So that most of the tops are produced unpolarized way, so that you can safely consider it as scale. So, but yeah, you're right. So that's really good point. Okay, so for those people, we went through some exercise. Okay, so then but still you can see from this figure this invariant feature in non-invariant energy distribution holds even with the polarities of different center of mass energies and types. Okay, so PP bar, PP, and different energy scales. Well, although of course the detailed shape can change, but you see the location P doesn't change, right? So it's the same. As another exercise, we try to prove the concept using 100 pseudo experiments under more realistic situations like realistic cuts and realistic statistics and detector resolution, etc., etc. Here's the sample pseudo experiment. Okay. So basically, the fits are the fitting procedure is done with these blue dots. Okay. Well, although I haven't talked about detailed procedure of the fitting because of time constraint, but then if you're really interested in I'm happy to discuss that issue after the talk. Anyway. So it turns out that the measured the peak value is consistent with the input value, okay? Which means the fit procedure is not spoiled by cuts or detector resolutions, okay? So the main message here is that the leading order effects are actually well under control, okay? So motivated by these observations, actually CMS is working on timeless measurement using this observation, okay, which is good. Okay, so far I have talked about only leading order result. Then one of the natural questions you may ask is what's going to happen to energy P once higher order effects can be taken into account, okay? So let me start from the production NL law. So you can understand this system as a recoil of the TT bar system by ISR. Okay. So then you can easily see that top quarks is likely to get more boost. Okay. So the boosted distribution top is picking toward the high the boost regime. Okay. And we also we tested with different values of initial state radiation, okay, so 20 GeV to 700 GeV, okay. So although the width of the distribution gets wider and wider as you increase the hardness of the initial state radiation, you see still the peak is invariant, okay. So in that sense, this energy peak is protected from initial state radiation. Okay. Now the question is final state radiation. Okay. So when it comes to final state radiation, the things gets a bit challenging. Okay. So you can understand the relevant event topology as a three-body decay of the top quark into a bottom W and gluon. Okay? It's effectively three-body decay. And then you can easily see that some fraction of bottom energy can be carried away by final state radiation jet, so that the peak actually shifts to the lower energy regime. Okay? So you can view the problem, in this way. So let's go back to the rest frame of the mother particle, which is top here. And then if you look at the energy of the visible particle, which is bottom, in the rest frame of the top quark, is the energy is given by a distribution. It's not actually fixed, unlike the two-body decay, right? So then, each value of the rest frame energy goes through a similar argument in two-body decays, like for E1 star and here, and E2 star, and etc., etc. Then basically we have to superimpose all the contributions, right? And then it turns out that the peak position is actually smaller than the maximum rest frame energy, as expected. Okay, and unfortunately, the energy, the location of the peak is highly model dependent. Okay, well, to retain the nice, invariant feature at the leading order, you could, neglect hard emission from a bottom quark using like jet B2 or something like that. And fortunately, our simulation study, detector level simulation study, tells that the energy peak is actually saved from soft radiation of bottom. Okay, and also typically higher order correction is suppressed by alpha star over pi. Okay, which means you can take it as small perturbation at the leading order phenomena. Okay. Okay, so far I have talked about the top mass measurement just as an example or test to prove the principle. But then these series of observations and exercises get it evolved into a serious measurement of the top. Okay, so for now we are really serious. So the question is why? My answer is why not? Okay, so theoretically, this method is supposed to provide a physical mass, like a time mass measurement using the endpoint of the kinematic variables, while other conventional methods like a template method provides Monte Carlo mass. Okay. Also, experimentally, this is supposed to give a difference in kinetics, and also it can be considered as independent measurement. Okay. So the bottom line is it's worth trying. Okay. So obviously, when it comes to a real situation, there are some challenges which are of course doable. Okay. So for example, three-body decay due to a finite state radiation, or the scale choice issue, or jet energy resolution, or jet formation issues, etc., etc.
Sorry, just want to make sure. So when you actually do this, the measurement, you want to know the energy distribution of the particle is from the decay that you want to look at. And then what's the conclusion about this soft radiation again? I mean, since I have a showering and I think you say the peak will shift and
Peak doesn't shift. I mean, it's
even is a FSR.
Yeah, even FSL.
Okay.
So the soft radiation doesn't make a significant effect.
Oh, that's not significant.
Yeah, I mean, at the theory level, it might affect the location of the peak, but then the simulation tells that actually effect is very tiny.
Well, the question is whether or not you can really tell when you do or don't have soft radiation versus hard radiation.
Right. So it's a combination of all of this.
Yeah.
I mean,
So I actually, that's the topic I'm going to talk about. So hard rate emission. Okay. Now let's talk about hard emission stuff. So in real situation, right? So jet definition is very important, right? So for some jets, the jets could be given by a combination of some different objects, like diagrams here. Right? So suppose you measure two bottom jets, okay, and here so ISL jet and FSL jet, okay. So you could measure this guy and this guy as your bottom jet, but then this guy contains the ISL, the initial state radiation, right? Or this guy is measured, but then the other bottom is measured in a way containing bottom and FSL, okay? Or you could just measure just two isolated bottom jets, okay? So then you can clearly see that even ISL could affect the energy, unlike the theory level consideration. Okay? So qualitatively saying, the large jet radius capture more FSL jets, definitely, right? But then the relevant energy distribution can be more contaminated by ISL jet, right? So your radius is large, and so that you can also think of this possibility. If you introduce small jet radius, okay, then you lose more FSL jets, but then the relevant energy distribution is less contaminated by ISL jets. Okay. So here's a simulation study with a small radius parameter. Okay.
Let me understand. So if you don't have any ISR jets, and you capture all the final state radiation jets,
Yes.
does that get you back to your ideal
Yes.
situation?
Yes. At theory level. Okay, so in this case, as I explained in the previous the slide, you can expect that less contamination by ISL jet, but then you lose more FSR jets. Okay, so that the energy peak is shifting to the lower energy regime. This is clearly seen from this figure. So this is the input, the mass versus measured the mass. Okay, so clearly you see that the measured value is a bit smaller than the input mass. Okay, and also it turns out that the NLO sensitivity to the scale choice is as small as plus minus 1 GeV on the time mass. So here's a simulation study with the large jet radius. Okay, so unlike the previous case, you can expect more contamination by ISL jets, but then you capture more FSR jets, so that the energy peak shifts to a higher energy regime, as is clearly seen from this figure, right? So input value versus measured value. So the measured value is a bit overestimated. Okay. And also, just like before, NLO sensitivity to the scale choice is as small as plus minus 1 GeV on the time mass. Okay. Here's another simulation study with the decent the radius parameter. So by definition, you can expect decent contamination by ISL jets, and you can also capture decent number of FSR jets. Okay. So maybe you can expect some sort of the cancellation between the two effects. Okay. So that there's no significant shift in the energy peak, as is seen from this figure. Right. So measured value is exactly the same as input value. And it turns out that the NLO sensitivity to the scale choice is as small as plus minus 0.5 GeV on the time mass. But for the moment, I don't know the deep physics of this, but there may be some conspiracy between the two effects, and so that the measured value is exactly the same as input value. But anyway, as far as time mass measurement is concerned, looks like 0.7 is kind of ideal choice.
Does it depend on the collider energy, or?
Oh, that's a really good question.
Or
Yeah, I mean we haven't tried yet. This is only tested with 14 TeV. But then I guess there's some sensitivity to the center of mass energy of the collider. But actually, the main message here is that doesn't matter, right? So given the radius parameter and given collider energy, so this is kind of relation between the input mass versus the measure value. So then by looking at this figure, we can easily make a correction, right? So how to interpret the measure value as the truth? That's the idea. Okay. So well, you can make some the theory argument. Okay. So I'm gonna try to parameterize some theoretical systematics by some small parameters. Okay. So here data production encodes the uncertainty coming from PDF uncertainty or new physics in the production level with the unpolarized top. Okay. And F pole encodes the uncertainty coming from new physics contribution with the polarized top. Okay. And here epsilon FSR is the correction factor evaluated from analog effect or jet pitot or something like that. Then you can easily see that the bottom jet energy peak correction is given by this relation. Okay. So these days, evaluating epsilon FSR is what we are working on. Okay. But one thing I want to emphasize here is that our method, for our method, the uncertainty, systematic uncertainty coming from the production level is actually suppressed by epsilon FSR. Okay, because by construction, our method, if you completely turn up the FSR, you can't feel the production level uncertainty. Okay, so the peak is invariant, right? So that's why this uncertainty can be felt through final state radiation. While other conventional methods, which consider full standard model, the matrix element, feels like a delta production. Okay, so in that sense, our method could be competitive. Okay, so that it can be considered as complementary method to complex measurement. Okay.
I'm not too clear on this. Yeah. So what is delta production is coming from what in the conventional methods?
So delta production is okay. So basically, you assume that the standard model top, right? But then still, PDF has some uncertainty, right? And you can also think of new physics contamination in the top production level. Okay, so that information is encoded in this delta production. Okay, so does that make sense?
Yes. Okay. I'm just curious. I guess I still don't see why your technique isn't sensitive to the same thing.
Okay.
You made it. I guess you tried to make an argument that there wasn't any PDF uncertainty, but there was.
That's right. So okay.
But
So
there's some boost uncertainty if the jet was hard.
let's turn up the FSR effect. Okay.
Mhm.
So my claim here was that the location of peak is invariant. I mean, it's exactly the same as rest band energy for whatever distribution is given. Okay. So you could think of very crazy boosted distribution, which contains the information about the production mechanism. But then, as far as you completely turn off FSR, the top peak stays the same. Okay, so in that sense, as far as peak position is concerned, you can't feel any of the production level the uncertainty. Okay, but then once you turn on the FSR, so FSR you have to think about the fraction of the 3-body decay. Okay, And this, three-body decay stuff can feel the production level uncertainty. So that's why, our method is the production level uncertainty is suppressed by
Okay, I see what
a
you're
fraction
saying.
of the FSR.
All right.
Okay, so let me switch over to the extra radiation. So as you see from the energy distribution, so sometimes extra radiation is problematic, so that it can be considered as ugly duckling. Okay, let's see how to transform them into a beautiful swan. Okay, so here's the situation motivating the use of the extra radiation. So this is disclaimer. This topic is more or less theoretical. The TW process is very difficult to distinguish from the TT bar because of severe interference issue. But then that's just some prescription was done, like a diagram removal or diagram subtraction stuff or something like that. Okay, so that's basic assumption. So, for example, you can think of the separating singleton production associated with the W gauge motion from the dominant TT bar background. Okay, like here. So then once one of the bottom is missed, then you can see that they are exactly the same in the final state, right? And they are very similar kinematically, right, to each other. So then it's very hard to come up with any killer kinematic variables to distinguish them from each other. Okay. So that's the challenging situation. I'm thinking. Okay, so eventually I'm going to use MT2 variable as a killer variable. Let me quickly go over the what MT2 variable is. Although the CTI knows the MT2 variable pretty well. But anyway, so MT2 variable, or as well as mass variable, is kind of generalization of the MT in this case where model particles are carefully reduced, and each model particle decays into a single invisible state plus visible states. Okay, so I'm not going to go over the full details of formalism. But then this variable is supposed to use global information. Okay, I mean basically it considered both of the decay size, and then this both of the decay size is connected by the missing it condition. Okay, and it turns out that the relevant distribution is bounded above, and the endpoint is given by the simple function of the mass parameters, like here. Okay. Once you include more than one visible particle per decay side, then you can expect that you have a richer structure, and you can expect more MT2 variables. Again, I'm not going to go over the details, but it turns out that various subsystems, you can think of various subsystems depending on particles whose mass is minimized and particles which are considered invisible. Okay, and for TT bar case, you can imagine, 3 symmetric subsystems and 3 asymmetric subsystems. Okay, so now let's talk about leading order process with respect to TW. Okay, so by definition, you can require one bottom text jet plus 2 opposite signed leptons. Okay, and then you can easily see that the observed bottoms and leptons come from the decay of the same particle in both signal and background. Okay, so that their typical momentum scale is very similar, and in turn, any kinematic variables processed with the visible form momenta are likely to develop very similar distributions. Okay, then you may wonder what's going to happen to the impact of the missing bottom jet for TT bar. Okay, and it turns out that that is actually translated into a reshuffling of the distribution of overall initial state variation, so that there's no significant impact on the relevant kinematic distributions. Okay, so no killer kinematic variables. So that motivates the machine learning the procedure, such as multivariate analysis at LS or boost decision tree at CMS. Okay. Here are some results using detector level simulation. Okay. So here I show the MT2 variable, MT2 distribution, and the invariant mass distribution formed by bottom and Lepton. So you see, so the signal and the background develop exactly the same distribution. So it's very hard to distinguish the signal from the background. Okay, just expect it. Now let's consider NLO. It's not actually NLO. It's not. The quantum correction is fully considered. So it's just the attaching an extra radiation. Anyway, so the main idea is to attach an extra jet into the leading order diagram of the TW process. Okay, so then you can require two bottom tag jet, one of which is coming from mis-bottom tagging, plus two opposite sign leptons, or one bottom tag jet plus one regular jet plus two opposite sign leptons. Okay, and then this additional jet requirement retrieves the leading order diagram of the TT bar. Okay, meaning that the relevant event topology is still well defined. Okay, so that the distributions in kinematic variables are still upper bounded. But when it comes to a signal, the relevant event topology is ill-defined because of the existence of initial state radiation or X-ray radiation. Okay, so that the distributions that can be stretched far beyond the TT bar endpoints. Okay, so basically the kinematic endpoints for TW process is completely dictated by the hardness of the initial state radiation. Okay. So here are some results. Okay, so there's the same variables, MP2 and invariant mass variables. And this is the signal, and this is the background. Okay, so this is for two bottom tangent plus two opposite, sign leptons. So you can see that large fraction of, signal events can be found beyond the kinematic endpoints for TT bar, which are denoted by, dashed lines here, right? So you see a large fraction of the signal events. Here are rock curves in background rejection versus signal acceptance. Okay. So we have tried a bunch of different amplitude variables plus the invariant mass variable, and then we found that the first four variables they show very nice performance, while the other two variables show decent performance. Okay. So for example, you can expect 99.5% of background rejection versus 5% of the signal acceptance, or 99% of background rejection versus 20% of the signal acceptance.
What is the bottom axis of these plots? I can't read from here.
Here, this one?
Yeah.
A signal acceptance. So signal accept. Sorry for the small.
So you're varying your signal acceptance by varying what? How far you are out on the tail, or what is your cut being used?
So you just vary the cut, and then.
So no, if you go back to transparency.
Yeah.
So you're varying where you are on the bottom axis of this
Right.
plot,
Right.
where the cut is.
So you just scanning over this axis. Okay. So suppose for example.
So where does in order to get 99%, where would you cut on that?
Oh, I see, some detailed value. Detailed value.
Yeah, right. Well, I'm just curious. How far out on the tail do you have to
That's
go?
a really good question. I don't remember the numbers, but those numbers are on on my paper, but I don't remember. But somewhere here.
So somehow this is based on the fact that somehow there's more initial state radiation for the single top production?
So the main idea is, okay, so you're doing some exclusive analysis, right? So 2 jets plus 2 leptons. But then, by that requirement, you can just retrieve the tree level diagram of the TT bar, right? So TT bar itself has 2 jets plus 2 leptons. But then, to have an extra jet for the signal, you have to introduce extra radiation, right? But then the relevant, event topology is ill-defined, right? But, the TT bar is well-defined, comes with, still well-defined, event topology, so that the relevant, kinematic distributions are upper bounded, still upper bounded, up to detector resolution. But then, the signal topology is ill-defined. And actually, the endpoint is completely, as I said earlier, completely dictated by the hardness of the extra radiation.
I'm sorry, I think I still haven't gotten I think I just haven't gotten the main point, because why is it that ISR is broadening the MT2 distribution for a single top and
It's the wrong topology.
Oh.
Yeah.
Oh, I see.
It's
You're
not-
using the MT2 appropriate for top.
Yeah, just
Yeah.
to kind
I
of.
see.
But what about other possible background? There are other background can give you 2 jets, 2 leptons, and
Yeah, but
Actually,
fortunately,
yeah.
this channel yet still, the dominant background is TT.
yeah.
So you could think of
always
like-
the dominant background, just
Yeah.
some
Well, as far as I remember, according to a CMS study, CMS and LS, both of the groups, they look at those channels, and then it turns out that the dominant background is TT, but other backgrounds are really, really limited.
So what is the acceptance? I mean, if you're out there at whatever it is, you can't see, maybe 200 GeV is your cut, how many events have you lost?
Oh, so here?
Yeah.
So,
Looks like you've lost most of your events, right?
yeah. So,
So is this realistic, I guess is my question? Is
Say like
something that
20%,
requires very
is it?
high luminosity or?
20% versus 99% of rejection. 20% of the signal events still survive,
I see.
versus
Okay,
you
so
can
that-
kill 99% of the background
Okay.
events. Okay, so there's another simulation study for 1 bottom type jet plus 1 regular jet plus 2 opposite sign leptons. Okay, so again you see large fraction of the signal events can be found beyond the kinematic endpoints for TT bar. Okay, and the rock curves tell us that okay, so you can the first using the first 4 variables, you can expect good the performance, while the other 2 show decent performance. But then you can see that there's slightly the worse performance than the previous channel. Okay, because in this case I'm not requiring 2 bottom type jet, so that even in TT bar it's likely to get contaminated by ISR jet, so that even TT bar, the endpoint, could be stretched far beyond the endpoint. Okay, so that's why the efficiency is a bit worse, but still it's good. Okay. And it turns out that this idea is actually can be applicable to a topology distinction between this and that. Okay, so the methodology is pretty generic. So you can think of this example even in new physics, like star pair production versus associated production of the star with Giardino, or Gluino pair production versus Gluino associated production of the Gluino with the S quark. Okay, So you can also find other good examples in other models. Okay. So the last ugly duckling. Let me talk about mis-bottom tagging, which is in progress. So here's the motivation. So given a signal process involving charm quark initiated jets in the final state, for example, you can think of a rare decay process of the top quark, okay? So which can be found in some of the Twix W models or multi-X W models. Okay, the charginal is charged Higgs decays into a CB bar. Okay. So by construction, its dominant background is semi-leptonic TT bar, like here. And given this, the signal process, the typical event selection would be as 3 bottom tagged jet plus 1 regular jet plus 1 lepton plus large missing energy. Okay. But then here the main idea is to increase the signal over background. Okay. So one more bottom tagged jet could be required based on the observation that mis-tagging rate for charm quark is much greater than mis-tagging rate for light quarks. Okay. So here's the bottom tagging efficiency, which is reported by the experimentalists. Okay. So they're roughly saying the bottom tagging efficiency is 70%, and mis-tagging efficiency for charm quark is about 20%, while mis-tagging efficiency for light quark is less than 1% or something like that. Okay. Now let me give you a very rough and optimistic estimation. Okay. So the main difference between signal and background is CB bar versus CS bar. Okay. Then the relevant signal over background for the case where you require 3 bottom jets is roughly given by epsilon B times 1 minus epsilon C over 1 minus epsilon S times epsilon C. Okay. But if you require one additional bottom tagged jet, then relevant signal over background is proportional to epsilon B times epsilon C over epsilon S times epsilon C. Then if you take the ratio of this guy to that and plug in the numbers given here, okay, you can easily see that the signal over background is increased by a factor of 25. Okay. Again, this is very rough and optimistic estimation. Again, life is not easy and there are some issues, right? So, as you see from the previous the slide, there's the PT and rapidity dependence of the tagging efficiency, okay, and definitely some combinatoric issue is there. And also you can think of charm quark tagging, okay. But maybe if charm quark tagging is involved, then it might be complicated. Okay, so you need to think about this charm tagging rate for bottom quark, and we have to simultaneously require the bottom and charm quark tagging techniques. I mean, basically it's complicated. Okay, and also you can think of small gap between top and charged Higgs. Okay, so in that case, basically the bottom is too soft to get detected. Okay, so then maybe the previous argument doesn't go through. And another issue is that once you require 4 bottom tagged jet, you have to think about other the background sources like TT bar, BB bar. Okay, so but anyway, so we are working on that. Okay? So here are some conclusions. So seemingly not useful variables techniques approaches can be reinterpreted as useful, of course with careful study, in the context of precision study and discovery potential. And 3 topics were discussed with physics examples in the top sector, so energy distribution, extreme radiation, and mis-bottom tagging. So the lesson from this talk is that you have more ugly ducklings, okay, which can be reborn as beautiful swans. Okay. Thank you.
Any more questions for Doojin?
So could you say again, why is the energy distribution ugly duckling?
Because, well, just explain. I mean, so at hadron colliders, as well as they typically don't look at energy distribution, even if they have the information. But because it's
they think
frame
it depends
dependent.
on the.
It's frame
okay.
dependent, right?
So they just don't measure
Right.
this.
So then they typically look at transverse momentum or transverse mass or something like that because it's insensitive to a longitudinal rules.
Yeah.
But then energy distribution, energy is different. So I think that's why the people, I think they look at it, but they don't look at it seriously.
I see.
Well, I guess the question is, which is a more efficient technique in the end? And I guess you haven't gone far enough yet to, in a practical situation, to decide whether your ugly ducklings are better than the MT2 ugly duckling or whatever, or have you? I mean, are you really, at this point, making a quantitative claim that you do just as well, or?
So we are, actually, as I said earlier, we are serious and we are working on, estimating the real game is okay. So once you go to LHS 13 or 14, then as far as I understand, statistical uncertainty is not an issue. The real game is systematic uncertainty.
Right.
Then that's why we are working on estimating the systematic uncertainty under more realistic situations. So the next, here I showed some results for NLO, but then we are planning to do simulation for NLO plus cartoon showering, and also another issue is that we did a simulation study assuming on shell top, but then maybe you might worry about the off shell top, so that the next to the list is do a simulation with the BW, not just the TTW.
I mean, there are also all these issues, like in experiments they use whatever, just particle flow techniques for
Yes.
constructing a jet and what have you. And I can't tell whether your technique would suffer from issues associated with that technique more or less than, say, MT2.
Yeah, so that's a really good question, and I thought that the experimenters are worried about the production level uncertainty, but somehow, in the TT bar, as far as I know, jet energy scaling is the dominant, the source of the systematic uncertainty. And then what they really worry about is, okay, so we are looking at just bottom energy, which is also jet, and then how that the error is translated into an energy variable or this technique. So if that is really comparable to other conventional techniques, or comes with really big uncertainty or smaller uncertainty, and they told me that okay, if this technique comes with comparable systematic uncertainty under 13 TeV and 3 years running, then it's really worth a try. So that's what I heard. But I think I'm pretty sure given this leading order plus the parton showering simulation, we have seen quite a increasing result. So that I guess this gives you at least gives you an independent measurement and complementary the technique. I mean timeless is very hard to measure, and this is my pure point of view. I think the more we have the independent method. So template method, or matrix of method, or kinematic endpoint method, or J-psi method, or the next leading order cross-section measurement, whatever techniques, as far as they are comparable, we should try. That's my feeling.
Are there no more questions for Doojin? Then let's thank him again.